So let me introduce myself. I'm Krzysztof Szarkowicz. I'm Principal Product Manager, but actually working in some solution groups. So we have some solution architecture team working on the transport architectures, focusing on the mobile transport architecture specifically, and the telco cloud. So we will be talking about Cloud Metro architecture, so including Cloud Metro for the business customers, Cloud Metro for residential subscribers, and Cloud Metro for the mobile transport. So going to more details. Legal disclaimer at the beginning. So I will be talking as well about some roadmap items, and Juniper is free to change these roadmaps. What will be actually implementing, not implementing. So some legal disclaimer about that. And the agenda for this short presentation is we'll discuss the Cloud Metro overview in general, what kind of use cases we have for the Cloud Metro, and then we'll go in more specific to different areas of the Cloud Metro. So as mentioned, business services is the first area that we'll be discussing. Residential services is the second area, and here we'll as well discuss in more details unified PON solutions. And the mobile 4G, 5G transport. This is three areas of the Cloud Metro that we're going to discuss. And of course, at the end, some case studies from the real customers, without naming the customers, of course, but something that we are working with their customers. So what is Cloud Metro? Yes, for traditional and emerging Metro use cases. So we divide Cloud Metro applications or architectures into three kind of use cases that we are addressing. One use case is business services. So we have a Cloud Metro architecture for the business services. So here we are talking about the Ethernet business services. So some sort of MEF-defined services like E-line, ELAN, so Ethernet and MPLS, high capacity, and as well some IP, so layer 3 services like IP, VPN, and IP services. Then SD-WAN and Cloud Connect, so interconnect the clouds. And here we are talking about additional services required or features required like telemetry, PTP, and so on. Then the second bigger use case or use case groups is residential services. So here we are talking about fiber to the home, so FTTX in general aggregation. And again, this aggregation could be using some E-line, ELAN service. So based on Ethernet and MPLS, it could be EVPN or VPLS. And as well, so, important here is the multicast as well, because we need to deliver typically to the residential services, residential subscribers, we need to deliver IPTV. So some multicast capabilities required, and PTP as well. The GPON, so we'll talk in more details later on about Juniper unified PON solutions. So how we implement that GPON, how we unify that, as well some cable. Yes, what's happening in the cable space when it goes to the Cloud Metro. And then the third one is the mobile transport. So here we are talking about 4G and 5G, especially 5G mobile transport. So 5G mobile transport brings new capabilities that are required on the transport, especially on the front haul side. So in 5G, we will discuss later on in the data. So we divide the 5G transport into three pieces: front haul, mid haul, and the back haul piece. And especially on the front haul side, we have very strict requirements when it comes to latency that we need to provide over the front haul, and as well when it comes to the timing and synchronization precision. So here we're talking about class C that is required for the timing synchronization, but I will talk later in more detail. So this is just a small introduction. And of course, on top of that, we need to have automation suite. And this is our Paragon Automation Suite. So in this presentation, I will not cover the Paragon Automation Suite, but Paragon Automation Suite will be covered later on by Peter in subsequent presentation, one of the subsequent presentations. All right, so let's start with the business services. So what we have in the business services. So basically, we see the transport network, the cloud network as converged metro. So basically, we have one transport, one converged cloud metro transport that's supposed to cover different use cases. As you see here, there's a transport, built from ACX and MX devices, and then we can connect different access technologies to this transport. That could be OLT, for example, could be some business access for the business customers, but could be traditional as well, more traditional DSLAM, CMTS, and so on. So we believe that the transport converged transport is the future story here. The physical topology of the transport in the Cloud Metro could be different as well. So here's an example of spine and leaf architecture. Then you have a couple of spines and a couple of leaves here and multiple leaves. But of course, depending on the layout of the physical requirements or physical constraints at given provider, given operator, could be different topologies. Yes, could be ring topologies. So ring topologies are very frequent as well, very frequently used. Or it could be some combination of ring topologies, spinal leaf topologies, some partial mesh topologies as well. So we are prepared for that on all fronts. And then, from the domain perspective, from the transport, what we see, the new emerging protocols that are emerging now as we speak is segment routing. Yes, all sorts of segment routing. So we're talking about segment routing traffic engineering, and topology independent LFA. So TLFA provides full backup coverage regardless what is the physical topology. So traditionally in the past, LFA had certain restrictions. It required nice topology from the physical perspective in order to provide 100% coverage. But with segment routing, introduction of segment routing and TLFA, which segment routing brings to the table, we have full coverage, full backup coverage. And then, in the DC domain as well, we are seeing introduction of segment routing capabilities and as well SRv6. So we're looking as well, some customers, looking for SRv6 in the DC domain to implement SRv6 in the DC domain. And then on the aggregation IGP domain, again, segment routing with different extensions, segment routing, maybe SRv6 as well. And then for intra-domain use cases, I will cover later as well in more data. So when the network is very, very large, and then we need to divide this network into smaller domains because of the scaling issues, of blast radius, of some failures, scenarios, and so on. So we're dividing the multiple domains. We are introducing here as well new capabilities like BGP class 2 transport. So I will mention that, discussing later in the data. And as well controller-based capabilities of creating end-to-end tunnels using PC controllers. So in our case, is Paragon Pathfinder, which will be covered in more details in some subsequent presentation. So business services. So as I mentioned, so the characteristics of the business services, we have basically, on the high level, two kinds of business services. One is the Ethernet business services. So this is the layer 2 kind of services, Ethernet-based services, and the models for these Ethernet-based services are defined by MEF, Metro Ethernet Forum. And here we are talking about E-line, which is point-to-point connection at the layer 2. We are talking about E3, which is point-to-multipoint connection at layer 2. And we are talking about ELAN, which is multi-point to multi-point connection on layer 2. And these connections could be implemented using different technologies. It could be implemented using VPLS traditionally, pseudo-wire emulation for the point-to-point technologies, and VPLS for some sort of multi-point technologies. But the emerging technologies which are emerging now is EVPN, so Ethernet Virtual Private Network, which very nicely implements all these different service models required for the layer 2. And again, the physical infrastructure could be span and leaf infrastructure shown here in the picture, or it could be some more advanced rings and so on. So when we talk about the migration, scenarios for layer 2 business services, so traditionally layer 2 business services are implemented using some sort of pseudo-wire emulation. So pseudo-wire emulation typically using LDP-based signaling. Or for the multi-point services is some sort of VPLS, so Virtual Private Level Switch Network. So with VPLS and some sort of hierarchical VPLS as well, that we have multiple pseudo-wire emulations, multiple pseudo-wires terminated in the VPLS instance. Now we are looking to implement this in the new way with the advance of EVPN, Ethernet Virtual Private Network. And here the question is about the migration from the old way, how we implemented in the old days and how we implement in the new days. And we are offering here different sort of options for supporting the migration. So basically, for the migration, when we support, for example, we support a configurable segment routing global base. So segment routing global base is some base used to So segment routing is basically a way to distribute the labels through ISIS or OSPF extensions. So there are IGP extensions to distribute the labels, as opposed to the traditional way when they separate protocol, like for example LDP, label distribution protocol, to distribute the labels. And then with distributing the labels over ISIS, we have predictive label values. So in LDP, these label values are some sort of dynamic ad hoc. So we don't know from the label value what is exactly meaning. With segment routing, we can configure base of the numbers that we use for the labels, and then we have very predictive labels. Okay. Then key features that are required for the migration scenarios for two business services as well is segment routing LDP migration in such a way that we implement a mapping server and mapping client. So mapping server and mapping client are used to map the labels between the LDP domain and segment routing domain. So in both directions. So one direction is mapping server and the other direction is mapping client. As well as on the forwarding plane, we introduced with this mapping server and mapping client features, we introduced as well, stitching at the forwarding plane level. So this is what is very important here. And there are a couple of another features, so prefix unicast seeds, so segment ID, static VPLS neighbors, and as well very important feature is seamless VPLS to EVPN migration. So basically, this is the feature that allows to create a single instance, and in the single instance, this is EVPN instance, but this EVPN instance can talk as well over VPLS to some legacy, PE, legacy routers using VPLS language, so to say. So this is single install can talk both EVPN language and VPLS language. So this is very important for the migration scenarios. So this is what we are introducing here. All right. So for layer 3 residential, for layer 3 business and residential access, we are introducing a couple of new architecture models. So first architecture model that I'm presenting here is based on the flexible cross-connect. As you see here, FXC is flexible cross-connect. So what does it mean, flexible cross-connect? So traditionally, when we create layer 2 pseudo-wire from one device, like here on the bottom, this ICX device, to some another device here on the top, some MX device. So traditionally, this layer 2 pseudo-wire needs to be terminated on single physical interface. Okay, and in that case, so here, if I have 3 physical interfaces, I would need to create 3 pseudo-wires to interconnect these 3 physical interfaces to the MX. So of course, if I think about large network with scaling requirements, this requirement, if I have here 48 ports, for example, on this box, on ACX 5448, I have 48 access ports, it would mean I need to create 48 pseudo-wires out of this single access device to some service device MX. So this creates scaling challenges if I have many access devices like that, and from every access device I need to create large number of pseudo-wires. So it might be scaling challenge on the service P and in that scenario. So we introduce a flexible cross-connect, which allows to cross-connects multiple physical, so traffic from multiple physical interfaces over a single pseudo-wire. Okay, this flexible cross-connect pseudo-wire, so flexible cross-connect EVPN-VPWS service, which are private wire service, allows to send the traffic from multiple physical interfaces. Okay, and only one instance here with multiple physical interfaces, and then pseudo-wire is attached to this one instance. So this is very important. Then another model as well that we introducing or we supporting is the multi-homing. Yeah, so we can have active multi-homing, as you see here. It's introduced using EVPN Ethernet segment identifier. So EVPN multi-homing, this is EVPN-based multi-homing. It could be active standby, but active is the most popular one. And then in that example, the PON device is connected to 2 access devices, 2 ACX access devices in active manner. On the PON device, it behaves like normal LAC interface, aggregate interface. All right, and then again is collected from 2 access devices, sent to some service PE. On the service PE, we are introducing as well the concept of pseudo-wire head-end termination. So basically, with pseudo-wire head-end termination, we terminate this pseudo-wire, regardless if this is, as I mentioned before, flexible cross-connect pseudo-wire, with EVPN service or plain EVPN pseudowire. We terminate that on the single pseudowire determination interface, and here we can extract different VLANs from this pseudowire to different services. As you see here, we extract some VLAN to VRF1 service, some another VLAN to VRF2 service, and maybe a third VLAN to some VPLS service. So it's a very flexible way of providing the services. So for another way as well, so we have as well more traditional with MCLAC, so multi-chassis LAC. Yes, with multi-chassis LAC, we can provide as well the similar services. Of course, there are some restrictions here regarding the flexible cross-connect, for example. And as well with multi-chassis LAC, we can provide active standby services, but otherwise the picture is very similar, the services we can provide. And then as well, another is for the layer 3 business access. Yes, layer 3 business access, again, we have only layer 2 on the access side to provide, active layer 2 access from the access device or FTTH device in that case here. And immediately on the access PE here, ACX access PE, we extract this layer 2 traffic into layer 3. So over IRB, integrated routing and bridging interface. Okay, with the integrated routing and bridging interface, to provide resiliency, this IRB interface on one access PE and IRB interface on another access PE is configured with exactly the same values. So you see this IP address is exactly the same, MAC address is exactly the same, which means if this FTTH box is doing some load balancing and so on, it doesn't really matter over which member link the traffic is sent, it will land on the same IRB from the FTTH perspective. And then IRB interface, this is layer 3 interface. This is some interface which is stitching layer 2 domain with layer 3 domain. Layer 3 domain, that is VRF. So IRB is placed in the VRF, and then from that point onwards, we send the traffic as layer 3 VPN traffic. Now quickly, let's go to the residential services. So let's discuss residential services. So again, residential services as well, the important is backhauling of the traffic, typically, some sort of backhauling of the traffic from the homes, yes, from the residential places, up to the places where we have some BNG, so subscriber management devices, BNG, or some cache servers and some internet. So this is typical way that we need to do that. And of course, here as well, we can do VPLS, pseudowire emulation backhauling, or the new one is EVPN-based backhauling. So let me discuss. And here as well, important some Q on Q, so double VLANs, because for the residential services, we typically have very, very large number of the subscribers. So with single VLAN, it would not be possible to transport all this traffic for subscribers. Single VLAN always only 4K subscribers. So we have support for Q on Q, and as well the HC snooping. So typically these residential subscribers, they will dynamically get IP address assigned. IGMP snooping for IPTV, for example, not every subscriber is interested in the same IPTV channel, so we need to have IGP snooping to snoop what IPTV channels are required for given subscriber. So what new features that we introduce? So features on ACX devices that we're introducing here to support this one. Again, so active multi-homing, EVPN active multi-homing, similar like we had in the previous slides for business subscribers. But in addition to that one, and then IRB as well, so IRB interfaces as discussed before. But in addition to that, we have advanced feature for the HCP. So we have the HCP relay on these IRB interfaces placed in the EVPN instances, as well as we have a synchronization of the HCP relay state between two access PEs. So because the synchronization is needed for the HCP states, eventually, if you like to do the HCP snooping on some DHCP-based protections, that's like, for example, dynamic ARP inspection. So if the access P on the left-hand side is distributing the IP addressing to the subscriber, then this information needs to be synchronized with the access P device on the right-hand side. So when for example, dynamic ARP inspection is in place, and the traffic is load balanced to the right access P, right ACX, this information is available here for dynamic ARP inspection. So this is what we introduce on these devices as well. And synchronization as well on the IGMP MLD states. So IGMP MLD snooping, this is for IPTV distribution. Again, if some IGMP, initial IGMP exchange was exchanged between the subscriber and the left PE, but eventually the traffic is sent over right PE, then of course right PE needs to have this state as well. So we need to have synchronization, and this is what we implement here as well. And last but not least is as well distributed access architecture for the cables, so the cable operators. So here we have different architectures that we are looking for. So first architecture is based on so-called remote PHY. So on remote PHY, we have a remote PHY device, and the remote PHY device is doing only very, very basic processing of the signal, yes, that we receive for the RFI signal that we receive for the coax cable. Is basically putting this signal in some sort of pseudo wires. So as you see here, DP is downstream external PHY interface. This is based on the IP pseudo wire. So putting the signal into pseudo wires and transporting the signal, for the core, for the converged cable access platform core, for the processing. Okay, and so the advantage of this one is that in this part of the network we can use IP network. Yeah, because here we can put the signal in some of IP pseudo wires, so MPLS pseudo wires, IP MPLS networks, IP MPLS pseudo wires. So we don't have a dedicated network here. Only in this part of the network you have dedicated this coax network. Another architecture approach is that some processing, some MAC layer processing that here in the first approach is in the central core site, is moved to the remote site. Okay, and that's the reason we call it here a remote MAC-PHY device. So here it requires more advanced device on the remote sites, but here we don't need to have any sort of tunneling as before. So before we had some sort of tunneling here, so IP pseudo wire, so it's normal IP traffic here already. And the third one is the virtualization. So basically this converged cable access platform in central location is being virtualized. So this, instead of having physical dedicated services here, we have virtual services running on the conventional Intel servers. And so we have virtual platforms. This is basically the same as Model 1. Model 1 and 3 are very similar, with the difference that here we have everything is virtualized instead of having physical devices. So what we see on the market, Model 1 is the most dominant, with the 3 is taking over. Yes, Model 2 is not so dominant. This is what we see, but 1, 3, these two models are pretty dominant in the market. And here, some more data of the use cases of this distributed access architecture use cases. So one very simple use cases is that we have this RPD, so remote PHY devices on the remote locations collected by the ACX, access devices, access PEs, sending some IP pseudo wire, and this IP pseudo wire is going to MX 10003. And here, is terminated, and then the traffic is distributed to the core functions. So this is very, very basic location. For this pseudo wire or this, signaling processing to work, we need to distribute as well the clock. Yeah, so that's the reason there's some grandmaster in the corner of the network. From the grandmaster, we are distributing the clock. The clock needs to be distributed to the RPDs, and as well needs to be available in the central location, because otherwise we cannot recover the signal. And now more advanced, depending on the size of the network, but in the remote locations and the central location, we could have more advanced here scenarios using some spine and leaf architecture, with the leaves being ACX and the spines being UFX. So the reason that leaves is ACX is because we need to have here some clocking, so some boundary clock is required here to provide the clock to RPD devices. On the spine, the boundary clock is not required. Here we are okay with the transparent clock as well. So that's the reason a cheaper device with low buffer and so on could be used. Otherwise, it's similar to the previous case. And of course, in more advanced, even more advanced scenarios, when the transport network, this central site is much far away from the remote sites, and there are plenty of remote sites, we could have even more advanced scenarios using, for example, the rings of DWDM rings, and with ACX 7100 routers, which recently were announced or recently were released, we can have colored optics as well. And with the colored optics, we can attach these rings directly to the DWDM, these routers directly to the DWDM rings. All right, let's go now for residential services. So residential services. For residential services, specifically for the unified PON solutions, yes, unified PON solution. So basically, what we are introducing is unified PON solution. What does it mean unified? Unified means that we have SFP, which supports OLT. So this is modular OLT. So SFP with OLT support. As you see here, this FFP consumes a little bit more power than the traditional SFP. That's the reason there's additional stuff for the cooling with this SFP, and these are radiators here for the cooling the SFP. Then we have Junos router when we inject this SFP, and broadband gateway somewhere that do subscriber management. All right, and then basically we are replacing a traditional way of deploying OLT networks that we have some edge or access router. And this edge access router is connected to some PON OLT shelf. In this PON OLT shelf is OLT termination. Instead of that, we have still our edge access router, which is ACX. So initially, we qualified this solution on ACX service, specifically on ACX 5448 initially. But in the future, we might qualify on additional devices. And here we inject this SFP class-based OLT devices directly into the router. Okay, so this is very efficient. Instead of having separate boxes, we have everything integrated into one box. So very efficient solution. And as I mentioned, initially we qualify this on ACXs, and we have three types of ACX 5448 specifically, and we have three types of ACX 5848. So ACX basic, ACX 5048. Then 5448D, which has the DWDM interfaces for the uplinks, and ACX 5448M, which has a MACsec support. Okay, so for all of these three types of 5448, this solution is qualified, is supported. Because of the cooling requirements or power requirements of these SFPs, as I mentioned, they consume more power than traditional SFPs. We can populate only half of the ports on ACX 5448 with this PON OLT SFPs. So which means we can populate 24 ports, 24 sockets, yes, with these SFPs. Remaining sockets can be populated with something with traditional SFP. And because of one SFP, one PON OLT SFP, we support up to 128 subscribers. So it means that one ACX 5448 can support up to 3,000 subscribers. And then subscriber management itself is, taking place on BNG on the MX broadband network gateway. So unified solution components, again, is SFP, which is injected into ACX 5448 router. So OLT-based SFP, this is one solution. Then we have controllers, so it's lightweight agent on the routers managing these SFPs. And there's as well managers, so central database, so software with the central manager software managing these OLTs from the central location. So there are the three components. And because of that, as you see here, that these components, we have a PON OLT injected in the ACX routers. Then we have some control processor, and the central manager to manage all the database from all PONs in the network, and BNG or virtual BNG as well to make subscriber management, and everything communicates over traditional IP/MPLS network. So we could have here traditional IP/MPLS network, whatever is so good could be shared. This network could be shared with other services used in the network. It doesn't need to be dedicated for the PON OLT. All right. And the last but not least is mobile 4G, 5G transport network. What we see in the mobile, what's happening in the mobile space when it goes to the transport and the radio as well itself, is the shift in how the radios are being built. So traditionally, the radios are being built in such a way that we have a remote radio head, so basically antenna on the top of the tower. and the bottom of the DAA we have BBU, baseband unit. So baseband unit is, processing the antenna signal, and it's locally on the same location. So antenna is the top of the tower, BBU is bottom of the tower, and let's say 80-90% of deployments is following this model today. Then some of the deployments are slightly different. In some of the deployments, we are putting away this BBU to some more centralized location. So the reason being is because in that case, this BBUs doesn't need to be hardened, because if I have centralized locations with 20 BBUs, I can have small central office, whatever, with proper cooling and so on. This BBUs doesn't need to be hardened. So the overall operational cost is lower comparing to the hardened BBUs at each tower location. And the communication between these BBUs and the remote radio head antennas is based on the front haul protocol, which is called CPRI, Common Public Radio Interface. So Common Public Radio Interface is some of circuit switch protocol. It's not Ethernet based, not IP based, not MPLS, nothing like that. It's circuit switch. It's something like TDM kind of protocol, something. Not exactly, but something like that. And there are strict requirements here. This BBU cannot be very far away from antenna, because otherwise the antenna signal cannot be processed correctly. So we are talking here about 10 to 20 kilometers approximately. So the reason being the latency between BBU and remote radio head, we are talking here about around 100 microseconds. So that's the reason that it cannot be. Because if it's more than this 100 microseconds, for example, 1 millisecond latency, we cannot really recover the signal. So that's the challenge. And we see, this 10% approximately deployments using this model. Now, this model is further changed by virtualization of the BBUs. So instead of having the physical appliances for BBUs, we are having some small data center with some Intel-based, servers. On this Intel-based servers, we are installing BBU applications, which are doing the signal processing. Of course, digital signal processing requires some special computation power, so these servers need to have some special hardware pieces for supporting this DSP processing. Okay, this is not traditional server, but with some additional hardware piece. Could be based on FPGA, for example, is this additional DSP processing capability, or GPU, graphical power, graphical processing unit as well. It could be used for that. And further, for 5G, what we are seeing is that further this component, BBU, is divided into two separate components. One component is called DU, so distributed unit, and another component is called CU, centralized unit. So DU component is strictly used to completely process the antenna signal, fully process antenna signal, and convert this antenna signal to IP packets. So extract, IP packets from that as an IP packets. CU is used more for the coordination between multiple antennas and so on. Okay, so that's the reason we don't process here antenna signals any longer. So which means these hardware requirements, what I mentioned before on the servers, are required only for the DU, as well as strict, clocking synchronization requirements are required on the DU as well. So basically, this is the challenge, or this is the difference that we see. Yes, eNodeB is distributed across the radio unit, distributed unit, and centralized unit, with additional pieces of the transport network, which is called front haul and the mid haul. And for the front haul, we have very strict requirements here, like 100 to 200 microseconds latency. Another requirement for 5G as well is very strict timing requirements. So here, time alignment error. This is timing precision required between two radio units, between the antennas. Again, depending what kind of radio features we are implementing, we try to implement, these requirements could be very strict. For example, a very typical requirements that we see today is here 260 nanoseconds on 130 nanoseconds between two antennas in order to implement these advanced features, like, for example, intraband continuous carrier aggregation in frequency range 2. Intraband continuous carrier aggregation is some sort of aggregation of the radio spectrum, radio channels, and it's required. We see the requirements as well for the transport slicing. So we see 3 different transport slice architectures or use cases. One is tactical link slicing, so which means we have one link and we like to channelize this thing somehow. Another is network sharing use case, when we have a network transport and we would say, okay, green operator can use 20% of capacity of this network, and red operator can use 50% capacity of this network. Yeah, this might be used, for example, for the RAN sharing. And in the RAN sharing, we have as well, so access network is shared between multiple operators. And then at the very end, we have, dynamic 3GPP end-to-end slicing requirements or use cases. So from the building blocks on the transport network, yes, what features or what the building blocks we have to implement the slicing and the Cloud Metro network. So first building block is some sort of isolation or separation of the traffic between different slices is required. This is being implemented using traditional VPNs. So nothing new here. So we have layer 3 VPNs, MVPNs, EVPNs, and VLANs as well, the access interfaces. So basically, this is business as usual. Then the second building blocks and second aspect of the transport network slicing in the cloud network is some sort of topology differentiation. So I have one physical topology, but out of this one physical topology, I can create multiple logical topologies. Okay. The third one is some sort of resource guarantees. So we need to provide some resource guarantees for the slices. And the fourth one, is the OM monitoring. So we need to monitor the SLA of the slices. And the fifth one is end-to-end orchestration, which will be covered in the subsequent session. So the mapping, and then specifically when we talk about the mapping of these slices to the 3GPP use cases, on the run side, the 3GPP, you identify the slices using SST, SD. SST is slice service type, SD is slice differentiator. These slices are mapped to some VLANs, and there's VLAN handoff between the radio side and the transport side, Cloud Metro side. And then, as I mentioned, so here we have these attributes like VPNs, some topology differentiation, and some resource guarantees. Recently, we introduced as well for topology differentiation a new feature in Junos. This is introduced in 21.1, so this is Q1 of this year. And basically, we are from Q1 this year, we are capable to do multiple routing tables per topology slice, per topology. So basically, we can create low latency tunnels using whatever SRT or FlexAlgo or RSVP, so low latency tunnels, and we install these low latency tunnels in this orange routing table. Then another set of tunnels, is created, optimized for the best effort, so high capacity, the best effort. These tunnels are installed in the green routing table, and so on. And then later on, when the traffic is mapped, this traffic is mapped on the additional attribute that is distributed with the layer 3 VPN prefixes, which is color extended community. So here you see color extended community is 1, so which means the protocol next stop for this prefix to be resolved inside of this routing table. So this will be used only this routing table here, the green routing table. All right, a couple of last few slides. So we introduced as well the new for the advanced architecture, multi-domain architecture, to create the slices across multiple multi-domain cloud architecture, so transport cloud architecture. New extensions to BGP, which are called BGP class for transport. So there's reference here to the draft. And this is basically enhancement of BGP-LU. So this is, like BGP-LU today with the addition of slice awareness so that we can create the, slices end-to-end using BGP class for transport across multiple domains. And as well, we have another option specifically for customers that are looking for end-to-end SRT calculations. So we have some optimized end-to-end SRT tunnels calculations when we optimize the topology database visibility from remote domains in order to scale this in the high level domains, and this is called express segment architecture. And we have traffic as well, introducing a new way of hierarchical QoS. So HCOS here. So with HCOS, we can create HCOS strategies over interface without the VLAN. So traditionally, we need to have VLANs here, sub-interfaces, and here with this HCOS, new HCOS, we can classify the traffic on the input, and then based on that, we can specify, attach HCOS on the output. And that's all what I wanted to present. So thank you very much.